When rigid frames are subjected to lateral loads, there are two different methods commonly used for approximate analysis of those frames. In this problem, we're going to perform approximate analysis using the Portal method. The key concepts we'll cover are making Portal method assumptions and constructing moment diagrams from internal loads at key locations. Our rigid frame has two stories, but the second story has only one bay. There are horizontal loads applied at each story, and we're going to construct a moment diagram for the girder EFGH. We'll do it by the following approach. First, we'll make simplifying assumptions. Step 2 will be calculate. Internal loads at inflection points. We pick the inflection points because there's no moment at those places. Then we'll be able to calculate some more internal loads throughout the girder and construct the moment diagram. Step 1. Make simplifying assumptions. And those assumptions will be: first, that inflection points are located at mid-span of all beams. Second will be that inflection points will be located at mid-height of all columns. Now, if the reactions at A, B, C, and D were not fixed, then we would change this assumption for the first story. But since we're considering these to be perfectly fixed, this will be our reasonable assumption. And our last one, interior columns each receive twice as much shear as each exterior column. Let's implement those assumptions. We'll have inflection points at mid-height of the columns. I'll label these K, L, M, N. Mid-span of the beams, P, Q, R. Mid-height of these columns, S, T, and mid-span of this beam, U. Now let's distribute shear to the columns. I'll cut the top story at inflection points S and T, and I'll draw that free body. And since these are both exterior columns, they'll carry identical shear. The total horizontal load applied to this free body is 8 kips. So when I apply horizontal equilibrium, eight kips minus 2 times the shear, we get a shear of 4 kips in each of the columns. So that means that the shear at S equals the shear at T, this one and this one, equals a positive 4 kips. Now I'm going to cut it at this row of inflection points and keep a free body of everything above that. We'll cut it at the inflection points. We have a shear we'll call V at the external column. Each internal gets twice that, and this external column gets a shear of V. We have a lateral load of 10 kips applied here, and that lateral load of 8 kips applied here. So I'll sum forces in the horizontal direction. We have the 8 kips and the 10 kips, and we have 1, 3, 5, 6 V coming back the other direction. So V is 3 kips. That means that the shear at K equals the shear at N, and that's 3 kips, a positive 3 kips. And it also means that the shear at L is equal to the shear at M and is equal to a positive 6 kips. Now we're ready to begin calculating internal loadings at the inflection points. And I'm going to draw a free body diagram of piece SIU. So I'll cut it at those two inflection points. And that piece is 6 feet tall, 10 feet wide. We have the 8 kip lateral load applied, unknown shear VU, unknown normal force NU. We know that our shear at S is 4 kips, and unknown normal at S. I can apply equilibrium. Let some moments about point U. We need to know all the internal loadings for this girder, which means I'll need to know the internal loadings at these inflection points. I really don't need them for U, so we'll sum moments about U. I'll choose counterclockwise as positive. We have the normal at S through 10 feet minus 4 kip shear at S through 6 feet. Everything else passes through point U. That means that NS will be 2.4 kips. Now we'll create a free body diagram of the other piece from the top story, U, J, T. It is also 6 feet tall and 10 feet wide. We have unknown shear at U, unknown normal at U. We know that our shear at T is a positive 4 kips. We have an unknown normal at T. So again, we'll sum moments. Because I don't need the internal forces at U, I'll sum moments about point U. This time, I'm going to reverse directions, and I'm going to choose clockwise as positive, because I think that'll be easier for my bookkeeping. The normal at T acts through 10 feet in the positive direction, and the 4 kip shear at T acts in the positive direction through 6 feet. Means the normal at T is a minus 2.4 kips. Now with the Portal method of analysis, we always have to start analyzing free bodies that only have 2 elements coming together. So we have to start in the corners. Otherwise, we have too many unknowns. Then we work inside after we have found internal loadings from the corner pieces. So now let's jump to piece KEP. Six feet tall, 10 feet wide. We have a lateral load of 10 kips applied to this piece. Unknown shear at P, unknown normal at P. Our shear at K we already found to be a positive 3 kips, but we have an unknown normal K. I won't need the normal in K to find the moment diagram for this girder, so let's focus on finding these 2 internal forces. I'll begin by applying horizontal equilibrium. We'll consider to the right to be positive. We have the 10 kip applied load, the 3 kip shear coming back at K, and the normal at P. Therefore, the normal at P is minus 7 kips. Now let's sum moments about point K. I'm going to choose clockwise as positive for this summation. The 10 kip applied load acts through 6 feet. The shear at P acts through 10 feet. And the normal that we just calculated is a negative and acts through 6 feet. So the shear at P minus 1.8 kips. Now let's move over to the other corner and draw a free body diagram of R, H, N. (10 feet long, 6 feet tall, with unknown shear at R, unknown normal at R, a shear at N that we calculated to be a positive 3K, and an unknown normal at N. So now we apply equilibrium. I'll apply horizontal equilibrium, and this time I'll choose to the left to be positive for our summation. It's my choice, and this makes my bookkeeping easier because both NR and the 3-kip shear are both to the left. The normal at R is a minus 3 kips. Now we'll sum moments about point N. And I'll choose counterclockwise to be positive in this case. We have the shear acting in the opposite direction through 6 feet, and VR acting in the opposite direction through 10 feet. So VR is minus 1.8 kips. Now we're ready to move deeper into the structure. So let's move to this piece. Piece L, P, F, Q, S. "10 feet on this end, 10 feet on that end. 6 feet tall there, 6 feet tall there. And this is point L. This is point P. This point Q. And this point S. If we look back at our previous work, we see that the shear at point S is 4 kips, and we found that the normal force at S is a positive 2.4. So we'll add that. To our free body diagram. Now let's look back to point P. And here we found that the normal at P is a negative 7 kips, and the shear at P is a negative 1.8 kips. So we'll add those to our free body diagram. Now at L, using the Portal method assumptions, we had calculated or approximated that the shear at L would be 6 kips since it's an interior column, but we don't know the normal at L. And we don't know the shear at Q or the normal at Q. So for our free body diagram, we have 1, 2, 3 unknowns. And the only ones I'm really interested in are these, because we're going to construct a moment diagram of the girder containing this piece. So let's apply horizontal equilibrium. We have a minus 7 kips. We have the 4 kips shear at S, the minus 6 kips at L, and the normal at Q. So the normal at Q is a minus 5 kips. Now let's sum moments about point L, since I don't need the unknown at L in order to construct my moment diagram. We'll choose clockwise as positive in this case. We have the minus 1.8 kips shear at P acting through 10 feet. We have in the opposite direction the minus 7 kips normal at P acting through 6 feet. We have the 4 kip shear at S acting through 12 feet. we have the shear at Q contributing in a positive rotation through 10 feet, and also in a positive rotation is NQ, but it's a negative 5 kips acting through 6 feet. Put all those together, we find that the shear at Q is a minus 4.2 kips. We now have the internal loadings at all of the inflection points along the girder, P, Q, and R. But we've not applied equilibrium to this piece at all. And I'm always looking for ways to verify my results. We've done a lot of calculations so far, and it's easy to make a math mistake. So let's use the free body diagram of M, Q, G, R, T as a check. So we'll draw that free body. This is 6 feet tall. This is 6 feet tall. 10 feet on this side. 10 feet on this side. This is point Q, point M, point R, and point T. If we take a look back at our previous calculations, we see that the shear at T is a positive 4 kips, and the normal at T we calculated to be negative 2.4. So we add those to our free body diagram. We look back at our previous calculations for R, and we see that we obtained a negative 3 kips for the normal at R and a negative 1.8 kips for the shear at R. And I'll add those to our free body. Down here at M, we used our Portal method assumption, and since this is an interior column, we assumed that the shear at M is 6 kips. We don't know the normal at M, and I want to calculate the normal at Q and the shear at Q to check our previous results. So let's sum forces in the x direction. I'll choose to the right to be positive. We have a negative contribution from the normal at Q, negative contribution from the shear at M, positive contribution from the shear at T, and drawn in the positive direction but a negative magnitude is the normal at R. Therefore, we calculate the normal at Q to be minus 5 kips. And if we look back at our previous slide, we see that we had calculated a minus 5 kips. Great. This checks. Now let's sum moments about point M. I'll choose clockwise to be positive. We have the contribution from the shear at Q acting in a clockwise direction through 10 feet, acting in the other direction but at a negative 5 kips through 6 feet, and that's our normal at Q. Then in the clockwise direction is our 4 kip shear at T through 12 feet, and drawn in the clockwise direction but a negative 1.8 kips shear at R acting through 10 feet, and drawn clockwise, but a negative 3 kips normal at R acting through 6 feet. We combine all of those to calculate a VQ of minus 4.2 kips. And if we look back at the previous slide, negative 4.2 kips is what we obtained before. Great. So this also checks. That's a good sign. Now let's focus on constructing the moment diagram. But before I can actually generate it, I need to know internal loadings at the rigid connections in the girder. So I'm going to start with a free body diagram of piece EP. We have an inflection point at the right side, and it was rigid connection at the left side. 10 feet long. We see from our previous calculations that the normal at P is minus 7 kips and the shear at P is minus 1.8 kips. So we update our free body diagram. We have our unknown shear at E, our unknown moment at E, and our unknown normal at E. I'll apply vertical equilibrium. Choose up as positive. We have the shear at E minus a minus 1.8 kips. The shear at E is minus 1.8 kips. Let's sum moments about point E. I'll choose clockwise as positive, and that gives me the unknown moment at E plus the minus 1.8 kips acting through 10 feet. So the moment at E, my moment diagram, will start at a plus 18 foot kips. Now let's draw a free body diagram of P to F, the other half of that beam segment. This is also 10 feet long. We see that the shear at P is minus 1.8 kips. The normal at P is minus 7 kips. We have an unknown shear at F, an unknown moment at F, and an unknown normal at F. I apply vertical equilibrium. And drawn up, but a negative quantity, is the 1.8 kips. And VF is drawn down. So the shear at F is a minus 1.8 kips. I sum moments about point F. I'll take counterclockwise as positive this time, so I've changed the direction I've chosen for positive because it makes my bookkeeping easier, I think. And so I have a minus, because it's not in that same direction, and a minus 1.8 kips through 10 feet, plus my unknown moment at F. So my moment at point F is a minus 18 foot kips. So if I construct a shear diagram for just the beam EF, a negative shear at the left end, midspan, and still at the right end. There's no applied load between E and F, so the shear diagram remains constant throughout, which means my moment diagram should have a constant but negative slope, therefore a linear shape. My moment at end E, we said, was a positive 18 foot-kips, so at that rigid connection it jumps to plus 18, and then it decreases linearly, and we calculated at the right end it's a minus 18. And we can check that. We have the shear area is minus 1.8 times 20 feet. When we take that, which is a minus 36, add it to the plus 18, we get the minus 18. Now notice, our work on this problem got a little bit easier. The length of GH is the same as the length of EF, and if we look back at the shear in R, it is also negative 1.8 kips. And since there is no load applied between G and H, it'll be a constant negative 1.8 throughout, which means that the moment diagram for GH will be exactly the same. So now we need only make calculations for FQG. So now we'll create a free body diagram of FQ. With an inflection point at Q and a length of 10 feet. We saw previously that the normal at Q is minus 5 kips and the shear at Q is a minus 4.2 kips. So we update our free body diagram and we have our unknown shear at F, moment at F, and normal. Let's apply equilibrium in the y direction. We have the shear at F minus the minus 4.2 kips. So the shear at F is minus 4.2 kips. We'll sum moments about point F, and I choose clockwise to be positive. We have the unknown moment at F, and in the positive direction is the negative 4.2 kips acting through 10 feet. So the moment at F is a positive 42 foot-kips. Now, free body diagram of the other half of the beam, QG. It is also 10 feet long with an inflection point at the left. We know that the shear at Q is a minus 4.2 kips. The normal at Q is a minus 5 kips. We have the unknown shear at G, the unknown moment at G, the unknown normal at G. So I'll apply vertical equilibrium. We'll choose up as positive. I have a positive but negative 4.2 kips minus the shear at G. The shear at G is a minus 4.2 kips. Now we sum moments about point G. And I'll choose counterclockwise to be positive. Get a negative contribution of the negative 4.2 kips acting through 10 feet, and a positive unknown moment at G. Moment at G is negative 42 foot kips, not the direction it was drawn. So we can now use this information to construct a shear diagram for the beam from F to G. We saw that at the left end, F, we have a negative 4.2 kips shear. That at the middle, Q, it is still negative 4.2, and at the right end, it's still negative 4.2. There's no load applied in between F and G, so we'd expect the shear to be constant all the way across. Now the moment diagram. Because the shear diagram is constant and negative, we expect the moment diagram to be linear with a downward slope. We see that the moment diagram starts at a positive 42 foot kips and ends at a negative 42 foot kips. With the constant shear, we should have constant slope, and that should be our moment diagram. Now, as a quick check, we have a negative 4.2 kips acting over 20 feet. When we integrate this, we get a negative 84 kips. When we take that negative 84, foot kips, add it to the 42, we get a negative 42. Good. Now let's consolidate this into one giant picture of the moment diagram for the girder. So we will construct our moment diagram, a unit of foot kips. We saw that our moment diagram rises to a plus 18, drops to a negative 18 foot kips, then rises at point F to a positive 42 and drops to point G where it's a negative 42, rises back to a positive 18 and drops to a negative 18 at H. Now let's go back and review how we got to here. We started by making simplifying assumptions associated with the Portal method, that the inflection points are at midspan of the beams and mid-height of the columns, and that interior columns each receive twice as much shear as each exterior column. We then applied those assumptions, labeled each of our inflection points, and then we distributed the shears to the columns at their inflection points. We then began calculating internal loading specifically at the inflection points. With the Portal method of analysis, we have to start at pieces in the corners, because otherwise we have too many unknowns. So we started in the second story in the top left corner and also found internal loadings for the top right corner, then moved to the first story left corner and the first story right corner. We then moved inside the structure and found internal forces at Q. We then used this other free body as a check of our calculations, because we've done many at this point that are prone to mathematical error, calculator error, and we found that it matched our previous calculations. So then we continued to find the internal loadings at the ends of the beam segments. We started at E and then moved to F, and we observed that because of the geometry of this rigid frame, GRH will be identical. We then moved to the interior beam, FQG, found the internal loadings at F and at G, and constructed our moment diagram for the girder. Well done.